The goal of this video is to compare and contrast the behavior of strong and weak acids when they're in solution to better illustrate why there are two different net ionic equations involved here. Many times you'll be given the reactants and asked to work towards products, just like we did in section 2.2. So the process we use there will still apply here. And if this slide might look reused, it's because it is reused. While we got fancy with this reaction type and made sure to state that the products of an acid-base reaction are always a salt and water, the products of an acid-base reaction are always a salt and water because that is what the double displacement process dictates. And both precipitation and acid-base reactions, and also the gas-forming reaction we'll see in a minute, all fall into this double displacement category. Again, we will follow the same process here that we did when predicting products in section 2.2. We will just want to add to our list that we need to determine whether we have a strong or weak acid with our strong base, as we will need to know that in order to write the net ionic equation. You will not have to predict the products of a reaction that contains a weak base as a reactant. You should be prepared to recognize weak bases though, because that will be free game. There are really two possible options for the net ionic equation for any acid-base reaction. The first option is that you start with both a strong acid and a strong base, and that you end up with one and only one possible net ionic equation. And that's the case here, as perchloric acid is a strong acid found on my list of 7 strong acids, and NaOH is a strong base. All of the ions that comprise these two species are present in a 1-to-1 ratio. Both strong acids and strong bases are strong electrolytes, so they will completely dissociate when I place them in water. None of the ion pairs will remain intact, so you no longer have perchloric acid or sodium hydroxide. You have only the ions that came together to form perchloric acid and sodium hydroxide, all of the time. With nothing but ions floating around in solution, it's easier for the salt and the water that are products of all acid-base reactions to form. The water will be formed when the proton, or the H+, from the acid comes together with the hydroxide, or the OH- from the base. For our purposes, our reactions will be done at a temperature that facilitates the formation of H2O liquid, or what you consider water. We will not form steam or ice. The salt will be formed from the cation of the base and the anion from the acid. This salt, for our purposes, will always be aqueous. So for our acid-base reactions, such as this one, we won't need the solubility table to determine the states of matter for our products. Woot woot for us. All of my ions were either plus or minus 1 here. So when I formed my neutral salts, my equation was automatically balanced for me. If that isn't the case, and it definitely can be that it's not the case, you would balance your equation at this point. Now that we have a formula unit equation, let's talk net ionic equation. I've color-coded the ion pairs in the formula unit equation for anyone that might be having trouble following what is moving where in our process. But remember that the majority of our species aren't pairs after being added to water. Instead, our reaction would be better represented this way. Notice that in all cases except the liquid water, I have ions floating around in solution. Much like we did with our precipitation reactions, we can take the important product, our liquid water, and locate the ions that went into the formation of that product. The other species are spectator ions that are not directly involved with the chemical change. Rewriting what is left, I end up with a proton and a hydroxide ion forming liquid water. All acid-base reactions that involve a strong acid and a strong base will share this exact net ionic equation. Even if the stoichiometry of your acid or base is not 1-to-1, by the time you balance the formula unit equation and then reduce the coefficients to their lowest whole number ratios for the net ionic equation, you'll end up at this same exact spot. Now, let's keep the base the same and change the acid from a strong acid to a weak acid. I know HCN is a weak acid simply because it's not on the list of 7 strong ones. This means that it doesn't behave the same way when I place it in water. It won't completely dissociate like the strong acid did because now I have a weak electrolyte. So weak, in fact, that if I have an acid that is very strong for a weak acid, still only about 10% of the molecules in the sample will fall apart. Our weak acids are much harder to wrap our heads around thought process wise because they're kind of like double agents and we have to consider them a couple different ways. The strong base is so strong that it will react with a proton or that H plus from the weak acid every time that it sees one. So we won't change what types of products are formed and we're going to stick with our salt and water. But the majority of the acid molecules will remain intact. And if I want my balanced reaction to best represent what is happening in solution, I need to leave them intact for that purpose. So our dissociated reactants look more like this than the 4 separate dots that we saw with the strong acids. Again, if only 5 to 10 molecules out of 100 are going to dissociate, then we need to think in terms of our weak acid as a unit instead of as its pieces. I still think about forming the products the same way though. The protons and the hydroxides will still form liquid water and the other ions will still form an aqueous salt. So the formula unit equation is handled very much the same way. The real difference in a weak acid-strong base reaction versus a strong acid-strong base reaction comes in the net ionic equation. Reactant side that is considered mostly intact, and liquid H2O on the product side that is in fact totally intact in this total ionic equation, which means that they need to stay intact when I move to the net ionic equation. Notice that I really only have one spectator ion now, as I'll have to include the cyanide in the balanced net ionic equation in order to balance my atoms. Yes, it is still aqueous, and in that respect it is still spectating, but we cannot destroy matter, so the atom count will win here.